And today I'm going to be talking about one of my favorite pinball related topics, and that is flippers. Flipper theory of operation and flipper repair. Uh, I guess I'll get a couple disclaimers and definitional things out of the way first. I'm going to be talking exclusively about flippers in solid state pinball machines. I'd say those from mid to late 70s on up through the present. And in that main umbrella category of solid state pinball machines, there's two types of flipper systems. I don't want to get the terms mixed up. Everything I'm talking about today is in solid state pinball machines. So when I talk about solid state flipper control systems, and when I talk about classic flipper control systems, I don't mean EM pinball machines. Everything's solid state pinball machines. But I want to touch on those two distinct categories of flipper systems in solid state pinball machines. And those are what I'm going to call classic flipper systems and solid state controlled flipper systems, where I'm going to call classic flipper systems those controlled by a flipper enable relay on a driver board or under the play field. And those were the standard in solid state pinball machines for the first dozen or in some cases even more years. And the solids, let me give you a few examples of the classic flipper systems first. You can see those relays on some of the driver boards. Gottlieb had them under the playfield. This is what enabled the flippers. So in any flipper system, but in this case, I'm going to talk about the classic flipper system first. The goal is to get the flipper voltage and a ground to the coil. That's where all the action happens. So just a brief summary of how that happens in a classic flipper system is power is always wired to the coil. Uh, this is the case in every manufacturer except Gottlieb. Gottlieb does it backwards. But in a classic flipper system, everybody else does it. The flipper voltage is always on the flipper coil. Doesn't matter if you're in game over mode, if you're in tilt mode, if you're in game mode. The flipper voltage is always hardwired to the coil. So the interesting thing happens in getting the ground to the coil to make the flipper energize. So in a classic flipper system, the ground is always going to the relay. And it's interesting that that little tiny CPU board there on the left is definitely not to scale. I should have made that bigger. Um, Basically, when you start a game, the CPU wants to energize that relay. So it does that. And now the ground is getting to the switch on the side of the cabinet. Now it's up to the player. When the player pushes that button, now the flipper flips. That's a pretty basic summary of what happens in a classic flipper system. In a solid state flipper system, flippers are controlled by a board. It might be its own separate flipper control board. It might be the main board that's just, transistor driven, just like any other coil. And in that system, the difference is there's kind of some magic going on behind the scenes. That flipper control board has some data going back and forth from the CPU, and it has the player input on the switch. I'm not going to go into too much detail on that, except to talk about that there is a little bit of magic going beyond the scenes here. If I had 6 hours to talk today, I could go into much more detail about some of these things. Or maybe I should say 60 hours, because there's a lot to cover everything. But before we get started with the actual seminar, I've kind of decided to do this in a question answer format, except differing from a normal question answer format, I'll be the one asking the questions, and I'll also be the one giving the answers. So you guys can sit back and listen. So here's a basic example of what I'm talking about with my question answer. And, people use the terms coil and solenoid. And technically, there are some differences. But in pinball land, everyone seems to use those terms interchangeably. A solenoid is just a specific type of coil, one that's used with a shaft that performs some mechanical work. But I'm just going to be using those terms interchangeably here and there. So the second basic example of what I'm talking about, and this will segue into some actual uh, good information, is when you see a flipper coil, what are all those numbers and letters on the flipper coil? Well, that's another thing that's broken up into two main categories. One is some of those numbers might mean the gauge of wire and the number of windings on the coil. And the other type is a part number, which doesn't have any meaning. It's just an arbitrary number the manufacturer came up with. And if they have a meaning, I don't know what it is. But examples of some of the ones that have the wire and number of windings on them will be some of these, where you can tell what the gauge of wire is, you can tell how many windings, you can tell if it has one or more coils built into it, and the part numbers are just some random numbers and letters. So this leads, the next question would be, if you looked at those numbers, you could see some of those have two coils in them. So why are flipper coils usually, not anymore, but they're becoming increasingly just one coil, but why do flipper coils, at least historically, have two coils in one? And that is because there are two distinct cycles of the flipper usage. You have the first cycle, which is the initial flip. That needs to be a high power coil. It has to move that flipper from rest. It has to hit a ball almost all the time. And you have the hold cycle. That requires far less power. And the important thing to remember is the high power coil draws so much current, you can't have that energized all the time. The coil would not last more than a couple minutes if it was energized all the time. So between the two systems of classic flipper systems and solid state control flipper systems, how are those distinct cycles managed? Well, in a classic flipper system, each flipper is self-contained. It takes care of that cycle change internally. It has an end of stroke switch. When the flipper gets to the end of its cycle, which is all the way up, the end of stroke switch opens. And in classic flipper systems, end of stroke switches are always normally closed, and they're always high power switches. And when they open, power is removed from the high power coil and resides only on the low power coil. In solid state flipper systems, this is all controlled kind of like magically on the board. Sometimes solid state flipper control systems have an end of stroke switch. Most of the time they do. Sometimes they don't. Sometimes they're normally open, sometimes they're normally closed, but they're always low power switches. So I want to give a few examples of high power versus low power end of stroke switches. You can see on the left, in fact, on the left there's one that's normally closed and one that's normally open. If you look at those contacts, they're normally gold plated. They're designed for low current applications. You could tell they're just not very robust versus the ones on the right. They're much more robust. You can just tell by looking at them that they're kind of designed for high power. They're typically tungsten plated, tungsten coated. Um, so the next thing I want to cover, when I was talking about the low power coil alone holding the flipper up, how does that work so well? If it's such a low power coil, how can just the magnetism of that low power coil allow you to catch a ball without having that flipper collapse? And how that's done is, in this example, I've taken the coil and the sleeve out of the picture. And when the shaft reaches the end of its stroke, it sticks to the end stop. The magnetism of the coil causes those two metal parts to stick together. And as long as both of those surfaces are flat and true, that bond can be pretty darn strong, even with a low power coil's magnetism. However, through use, that flat and true surface on both of them just doesn't last that long. So by the time that flipper shaft and end stop have smashed together thousands of times, which happens pretty quickly, when you try to catch a ball, the flipper will partially collapse before it recovers. So the question is, can't you just file those surfaces when they wear out like this and make them work better? And the answer is, yeah, you can do that, but keep in mind a few things. Number one, it depends greatly on how good your workmanship is. You're not going to be able to get those flat. You know what? Before I continue on this, I just remembered I should have included a slide. I'm going to back up to this. If you look at that flipper shaft in the left picture, I guess this one only has one picture. You can tell there's a bevel on, you can't tell so much on the end stop, but you could tell there's a bevel on the end of, probably a 45-degree bevel on the coil shaft. And that is because when these parts collide together thousands of times, without that bevel, the end of the shaft would start to peen over. And that would cause a lot of restriction in as the coil slides through the shaft. So it's necessary with new shafts and well-working shafts to have that bevel. Because if you look at these pictures, that bevel is almost gone. And in fact, if you look closely, you can see those flipper shafts are peened over. They'll be rubbing on the inside of the flipper shaft, on the inside of the flipper sleeve. So where were we when trying to catch a ball? Okay, can't you just file these? Yes and no. It's difficult to get them to be perfectly flat. It's difficult to get them to be perfectly true. So another thing to keep in mind is when you file those down, you're shortening them. And when you shorten them, that's going to increase the travel that the shaft has. And it'll make your flippers not match position-wise. But also, once you file those too much, I'm going to give an example of what will happen. Once you file them too much, this will be an example of why not to file them. This link and shaft came out of a pinball machine that somebody filed down. And after they filed those parts down, there was more travel with the shaft than there should have been. And even after they filed them down, the parts wore some more. So this happened. And the way it happened was the shaft and end stop were so short, the shaft could no longer reach the end stop. So that nylon link was actually bottoming out against the bracket that holds the flipper. And eventually, of course, that wore. And I imagine in this game, the hold power was pretty weak since the shaft could not mate against the end stop. And here's what those shafts and end stops look like when I took them out. You could just tell that somebody's been doing a lot of work on them, and even beyond that, they were worn. So the next question, I wish more people knew the answer to this question. As many flipper assemblies as I've worked on, I wish more people knew the answer. But to give my answer, I'm going to defer to my great-grandfather, Aloysius Gullo. You can kind of see the resemblance there, can't you? So what he used to say on this topic was, "Lubeth not thine battaloons, lest ye succumb to ill fate." Battaloons. I think that's what they used to call flippers back in the old country. So what Aloysius was saying there, in his own way, of course, was don't lube your flippers or you'll make things worse. And that's because flipper mechanisms were designed to be run dry Flipper mechanisms work best when run dry. So if you're ever in a situation where you're thinking, I think my flipper mechanism needs a little lubrication, don't do it. Instead, you should be thinking, what should I do instead? And what you should do instead is you should be cleaning these parts. You should be cleaning the outside of the flipper shaft, the inside of the flipper bushing, the outside of the coil shaft, and the inside of the coil sleeve. And doing these things, this is all you ever need to do. I like to use isopropyl alcohol. It's a really good solvent for all sorts of grease and grime and flipper shaft dust. It dries quickly, does a good job cleaning. And some of these metal parts might need a little more than that. If you have some of these metal parts, like that flipper shaft in this picture looks a little rusty, that's going to need a little bit of fine steel wool. So doing these things in conjunction with replacing worn out parts and doing all the proper adjustments, in the vast, vast majority of cases, that's going to take care of any flipper sticking or weak flippers. Now, that said, there is a place on some flipper assemblies to add lubrication. I know Ron's sitting there in the front row. Every time I tell Ron this, he's like, what? What? You're going to lubricate your flippers? And then I'll show him. He's like, oh, yeah, I remember. So if you have flipper springs like this, where the spring is not on the flipper shaft, it attaches at both ends to a little hole in a bracket, I contend that you should put a tiny drop of oil at the end of the spring inside those holes, lest ye succumb to this. This will eventually happen because every time the flipper flips, that spring moves ever so slightly. And I've seen these holes worn everywhere in between the pristine hole that it started with and this completely worn through. It might take a couple decades for it to happen, but I always put a tiny drop of oil on the end of those springs. So before we actually get to the next parts, I want to talk about a couple, three actually, three important characteristics of coils. Now, the first one, this is not going to be earth-shattering to everyone. Everyone that's ever done anything with a coil knows that when you apply a voltage to a coil, current flows in the circle around the coil, a magnetic field happens. And that causes some mechanical work to happen. That's not earth-shattering. Now, the next two, I think, are the interesting characteristics of coils. And that is, when you first apply a voltage to a coil, the current flowing through them spikes very high for just a split second. And then it returns to normal. And the second interesting characteristic is when that magnetic field collapses, when you remove the voltage from a coil, a very high voltage pulse is emitted by the coil. So we're going to refer back to these in the next few questions and answers. I just wanted to state those here to start out with. So the next question is, what type of fuse should be used for flipper voltages? Well, let's go back to that first of the interesting characteristics of a coil. The current spiking very high when you first energize the coil. So for flipper fusing and for any kind of coil fusing, you should use a slow blow fuse. In fact, you need to use a slow blow fuse. If you don't use a slow blow fuse, you have two options. You have to put up with some false blows where there's no problem, or you have to increase the amperage rating, and that would not be very protective. So always use slow blow fuses in coil circuits because of that first characteristic. Now, the slow blow fuses, they'll have ratings if you look at the specs. they'll be able to withstand 200% of their rated value for a second or two. They'll be able to withstand 150% of their rated value for 500 milliseconds. Now, I just made those numbers up, but that's kind of what the ratings talk about. And like I said, some of the original pinball manufacturers used to use fast blow fuses, but they typically had to overfuse them to get around that high current spike, and that made them less protective. Okay, so we're going to talk about another one of those interesting characteristics. When I asked the question, what is the purpose of the diodes on flipper coils, or any coils for that matter, but in this case we're talking about flipper coils, we're going to go back to that final interesting characteristic, the one where the magnetic field collapses and the coil emits a high voltage pulse. That's where the diode comes in. The purpose of a diode on a flipper coil is that it keeps that high voltage pulse looping back through the flipper coil until it's dissipated. And why is that important? That's important because solid state circuitry wants nothing to do with high voltage pulses anywhere around it. And it's also why coils in EM pinball machines don't need diodes, because there was no electronic circuitry to have to worry about. In fact, the diodes are so important on coils. If I ever see a game rebooting, if I ever see a game crashing, locking up, my first thought is, I wonder if there's a broken diode on a flipper. It could be a broken diode on any coil, but flipper coils get used more than any other coil. Flipper coils are stronger than any other coil. So they're the ones that typically have the diodes break. Okay, so, also, I did mention that every coil in a solid-state pinball machine has to have a diode. Normally, the diodes are mounted directly on the coils, but not always. Sometimes they're mounted remotely. Could be on the driver board, could be on some sort of an interconnect board, but every coil in every pinball machine, every coil in every solid-state pinball machine has to have a diode, or you'll have games rebooting. Okay, that brings up the next thing is when pinball machines, solid-state pinball machines, first came out, they typically had the coils mounted in this direction, where the lugs and the diodes were on the end stop side of the frame. And sometime along the way, I don't remember exactly when this happened, probably in the 80s, they started reversing them because they were finding that the highest vibration area is where the coil slams into the end stop. So they started reversing the coils like this. And I would recommend always reverse your coils so they're mounted like this. Not just because the diodes will break less, but the wires will break less. Now, there's some times when you can't keep a coil mounted in this direction. There might be a problem with the lugs interfering with something else. In flippers, that's not going to be the case, but I just was working on another game just yesterday that I couldn't mount a coil like this because it was in such tight quarters. But typically, you would always want to mount your coils like this. Okay, we're going to go back to that other interesting characteristic of a coil again. When I talk about how are flippers managed when there's more than one flipper on a side. And that's important because you don't want more than one flipper on each side energizing their high power coil at the same time. And why not? Well, that would put a lot of stress on a lot of the parts. Number one, it would require a much larger fuse. If you had 4 high power coils firing at the same time versus 2. And it would also stress the power supply, which generally is just a bridge rectifier. And also the cabinet switches that the player actually pushes the button. Those would have twice as much, or more if you had more than 4 flippers. Those switches would have twice the power going through them, limiting their life. So how did pinball manufacturers get around this problem. What they did was they staggered the firing of the high power coils between the lower and the upper. And how did they do this? It's not detectable to the player, but how did they do this? Well, in classic flipper systems, they would typically add a second switch on top of the end of stroke switch. Sometimes it was done on the cabinet, the flipper button on the cabinet, but usually it was a second switch mounted on top of the end of stroke switch. And that switch was always normally open. And when the flipper flipped, it would close that second switch, causing the upper flipper to fire its high power coil. And I'm going to give an example of this in a minute. But in solid state flipper control systems, this is kind of all happens behind the scenes. It's kind of like magic to the player, to the repair technician, until there's a problem. So this is how they handled it. This is an example of a lower flipper that has its normal end of stroke switch. It also has a second switch. When that second switch closes, the upper flipper fires. This happens so quickly, it's not detectable by the player. The player thinks they're both firing at the same time. Now, I'm going to show another picture here of the coil shaft mid-cycle. And you can see the second switch is starting to get near closing, and the end of stroke switch is starting to get near opening. But the second switch can't close until the first switch opens. And in the next picture, you'll see that cycle is complete. The shaft is all the way in, the end of stroke switch opened, removing the high power from the lower coil and applying it to the upper coil. So next, why do some flipper coils have one diode and some of them have two diodes? And I'm going to link that to the next question. And I'm going to answer the next question because it'll make the answer to this question obvious. But the next question is, what is the difference between parallel and series wound coils? And answering this question will answer the prior question. So series wound coils were the standard in solid state pinball machines for a dozen years. The first one I can remember would be in the late 80s when the parallel wound coils came out. I remember F14, Williams System 11A, might have been the first one that I can remember. Well, in the original types, the series wound coils, both coils were in series for the hold cycle, making the hold cycle just a little bit weaker when you have two coils in series. And the high power coil was the only coil energizing for the flip cycle. Series wound coils can have two diodes, but I would contend they only need one. A lot of pinball manufacturers still put two diodes on them, but some didn't. But series wound coils only need one diode. Some of them have two. Parallel wound coils, like I said, started in the late 80s. They're a little bit stronger because of that parallel nature. The flip cycle has both the high power and the low power coil both energizing at the same time in parallel. So they're both assisting that initial flip cycle. And they're also a little stronger on the hold cycle because the coils are not in series on the hold cycle. It's only the low power coil that's energized. So parallel wound coils make both cycles just a little bit stronger. And parallel coils always have to have two diodes. So if you look at a coil and just look at how many diodes are on the coil, you can't really tell if it's a parallel wound coil or a series wound coil. You would have to look closely at how the end of stroke switch is wired and how the coils are wired. I remember Williams System 11A, the flipper coils they used to use are the same number of windings and the same gauge wire as the System 11A parallel wound coils. They just have the lugs wired differently internally inside the coil. So that kind of, I think that answers why do some flipper coils have one diode and others have two. And that is because some of them are series wound coils, some of them are parallel wound coils. So moving on to the first real adjustment. How and why do you adjust the bushing lash in flipper mechs? And when you first hear that, you're probably wondering, what the heck is bushing lash? And I don't know if anyone else uses this term. This is what I call it. I have a flipper assembly here, kind of taken apart, removed from the playfield. You can see the flipper bushing in the middle. You can see the flipper sitting on top of it, the crank arm down below. In my example here, there's no gap, top or bottom. This flipper system, the way this is, this would not work very freely. Both those upper and lower parts would be rubbing against the bushing the whole time. So somewhere along the way, somebody came up with this interesting tool. They came up with this little piece of plastic. It was used to adjust that gap, the bushing lash. And the way this works is you can use this on the top of the playfield or on the bottom of the playfield. You can't use it in both. The total gap in that vertical system has to be the thickness of that adjustment tool. And I'll show here, there's a picture on the left that shows that tool being used on the bottom of the playfield below the bushing, and then you could do it on the top of the playfield too. Now, I typically don't use this tool because I've adjusted this on, I can't even tell you how many flippers. So I kind of have a feel for how it should be adjusted. But basically, you have to make sure the crank arm is not tightened onto your flipper. You put this adjustment tool in top or bottom. You squeeze the two together to get out the rest of the gap or the lash. And then you tighten up the nut or the set screws onto the flipper shaft. And when you remove the adjustment tool, the gap is set. Now, that doesn't mean that's the gospel, that's the gap you want to leave there. That is typically the gap you want to have in that system. However, there are times when you have to tweak it. You're almost never going to tweak it to cause the gap to be smaller. Every now and then, you might want to make the gap slightly larger. But again, you don't want to make it too large because, as you'll see in this picture, I intentionally made this gap about 6 or 8 times as big as it should be. And you can see what happens with the alignment of the crank arm and the link and the shaft. This flipper will almost certainly flip, but it almost certainly won't return from its upper position. It'll be so bound up. So consider that gap that the adjustment tool provides to be a good starting point. And generally, that's where you want to leave it. But you want to make sure that the flipper assembly is working freely with that amount of gap set. And if you look at the alignment of the crank arm and link to the shaft, you can see whether that alignment is optimal. You might on occasion have to increase that gap, but typically that gap is the thickness of the adjustment tool. Okay, so let's move on. Another question I wish more people knew the answer to. And it's also a question that is kind of, I'll ask 2 questions and I'll answer them, both of them the same. So we'll just put those 2 questions together because the answers, well, the answer of how not to do it and to how to do it is the same answer. First of all, I want to talk about how not to do it, which also happens to be the way I think most people do it. You should never grab the flipper and make it go to the end of its cycle, and then check the adjustment of the end of stroke switch while you're holding that flipper bat up. You should never do that. And likewise, in the picture on the right, you should never check the flipper position adjustment by holding the flippers up. And why don't you do it that way? Well, the answer is when you do this, you're not taking into account any wear of any of the components. And also, even if you had brand new parts in there, every part has a little bit of play in it. Even the new parts, they have to have a little bit of play. And when you're doing this, you're not taking into account all that play. So here's an example of something that's worn out. You can see in this one where that crank arm engages in the flipper shaft, the nylon is almost completely worn off. So if you were just turning the flipper bat by hand, you're not taking account of any of this. So your adjustments will not be accurate. So what should you do instead? This is what you have to do when you're adjusting an end of stroke switch. You have to actually take your finger and push the shaft all the way into the coil till it bottoms out against the end stop. This is what the flipper is doing. This is what the flipper coil is doing. This is the only way to do these adjustments. It's the only way to do them properly and accurately. It's hard to do. If you're trying to adjust flipper position and you have the playfield down, you have to reach up through the coin door, find out where is that shaft on each of them, pull them in both together, and then kind of look up top and see the adjustment, but that's how you have to do it. It's the only way to do it accurately. And also I want to mention how to set the gap on the end of stroke switch. I like to start at about 1/8 of an inch. Uh, the smaller you make that opening gap at the end of the cycle, the smaller you make it, you can make the flipper a little bit stronger if you make that opening gap slightly smaller, because that would mean that the high power coil is energized for a longer period of time in the flipper's throw. But I don't think you want to do it because the power gain is negligible and you're kind of risking, if you have that switch only opening ever so slightly, you're at risk for having that coil energized too much or too long. But even more importantly to setting that opening gap at the end of the cycle, at the end of the throw, is you want to make sure those end of stroke switches are closing properly. You don't want them to just merely touch. There's a lot of current flowing through those end of stroke switches. When you see that end of stroke switch close, it needs to close and then go a little bit further. The blade that moves needs to actually move the blade that's stationary. Then you know you're getting a good connection there. So the next question, why do some end of stroke switches have capacitors on them? Like in this example, you see that big yellow Mylar capacitor mounted on that bracket. It's connected to the end of stroke switch. So what's the purpose of that? And the purpose of that is when a switch has a lot of current flowing through it, at the moment it opens, you'll see a spark. Not at the moment it closes, but at the moment it opens, you'll see those contacts arc. And that capacitor absorbs much of that arcing. It lengthens the lifespan of that end of stroke switch. And if any of you in this room are old like me, you might remember conventional ignition systems in cars. Underneath that distributor cap, they had a set of points. And in those systems, they had what they called a condenser. And that condenser was just a capacitor doing exactly what this one's doing. And when your condenser went bad, the points in your ignition system would also go bad very quickly. In fact, if you had a set of points in your ignition system going bad frequently, this was the cause. That condenser was bad. And I would contend that every classic flipper system with high power end of stroke switches could benefit from this capacitor. But you won't see it on too many. There were a couple manufacturers that use them. What value? Typically, they're 2.2 microfarads, and they're typically a very high voltage also. Something like 250 volts. I think that's the standard, 2.2 microfarad, 250 volts. Okay, so this one might sound a little silly too, but what is the purpose of a coil sleeve? And I'm going to touch on a couple of the basic ones. Yeah, they protect the inside of the coil. Not necessary, but they do. And they make replacing the coil sleeve a cheap and easy alternative to if the inside of the coil itself would get damaged. But the most important purpose of a coil sleeve is they keep the coil shaft aligned with the coil. And in this example, you can see I've removed the coil, but I've left the sleeve. In this example, the flanged end goes firmly over the outside of the end stop core, and the other end, the non-flanged end, has to go through the hole in that coil holding bracket. And this keeps the coil perfectly aligned with the coil shaft. So I would say that is the most important purpose of a coil sleeve. And everyone's probably heard of flipper rebuild kits. And I actually love flipper rebuild kits. You get all the parts you need. They're pretty affordable. Most systems are pretty affordable. Um, However, I've come across some situations where they aren't perfect, and I wanted to touch on a few of those. Some of these are maybe slight gripes, and some of them are just things to watch out for. But some flipper rebuild kits come with new bushings, and some don't. So depending on who you order the kits from, you might get the same kit from one source and the same kit from another source. One might come with bushings and one doesn't. And since we're on the topic of flipper bushings, some flipper assemblies, Williams was one that came to mind right away, they always had nuts on the bottom side of the flipper base plate where the bushing screws were. I always remove those nuts. But when I put the bushings on, as you can see on the right, I do use Loctite. And the reason why I never ever put those nuts back on is if you have a flipper assembly in a game and you need to replace the bushing, if you had nuts on the bottom of it, you would have to take the whole base plate off to get those nuts off before you could change the bushing. So, other concerns about flipper rebuild kits. Oh, I've rebuilt, I should say, a lot of classic Stern flipper assemblies. And I wish I had a better picture of what I'm about to describe here. But whenever I buy classic Stern flipper rebuild kits, for a long time I had a problem. And if you can see, there is a link and a washer and a E-clip holding that on. And in its usage in a game, this is upside down, so the E-clip is on the bottom. But the slot for that E-clip was so thick that the washer could slip down into the E-clip slot. And every time it flipped, it caused that washer to wear in a funny way that made it extra thick. And in not too long of time, it would cause the flipper mechanism to bind up. So I don't know if you can tell in this picture, but the fix for that was I added a second E-clip and it took up that extra gap, and now the washer can't get down into that E-clip slot. So if you're using classic Stern rebuild kits, add the second E-clip to hold on that link. And while we're talking about classic Stern flipper rebuild kits, I've done this myself. When you order them, they come in different styles. They come, sometimes they'll come with all 632 holes. Sometimes they'll come half 632. Sometimes they'll come half 832. I try to always order the ones that are half 632 and the ones that are half 832, but sometimes I've ordered the wrong ones. So I have to drill out the holes that I need to use with 832 screws. More thoughts on flipper rebuild kits. Okay, Williams used throughout the years 3 different size end stops. They're interchangeable, but the height of the core was different. In their early systems, system 6 through maybe 11, yeah, 6 through early 11s, they used the silver core end stop. And that was only 6.3 millimeters tall. And then for a while, from that point on through early, maybe to WPC, they used the gold color core end stops. Those were a little bit taller, gave you a little bit less throw in your flipper cycle. Then they went to the standard black one, which was 8 millimeters tall for the rest of the way. And that's actually a little bit less length of the stroke. But whenever I order flipper rebuild kits for Williams pinball machines, it seems like anymore, all I ever get are the black 8 millimeter ones. And I've always been a stickler for trying to keep the parts what they were originally designed to be. So over at past times, we order enough flipper rebuild kits where I do some special orders with some of the manufacturers to make sure I get a certain amount of 6.3s and a certain amount of 8s and 7.3s. And you can see in my flipper, my rebuilt flippers that are ready to go in games, once I mount that end stop on the flipper assembly, I always mark it on the outside what the height of the core is. So at a quick look, you can tell what it is, and you don't have to take it apart to see what color it is. So my next complaint about flipper rebuild kits, and this might just be a confirmation bias because I've had a few bad ones, but I wonder about the quality of the parts. I've seen, it seems like quite a few problems with what I'm suspecting are inferior parts. I've seen nylon links breaking prematurely. In this case, the end stop core just fell off. It wasn't even that old. Just various things like this. So while I love flipper rebuild kits, they're not perfect. So let's move on to, everyone's probably seen this. This is what people seem to do when they get an end stop screw stripped. Just grab a bigger sheet metal screw and kind of wedge it in there. And the one on the left, you can see one of them broken off. The one on the right is just wedged in there, probably not tightened all the way because the screw is so long it was going into the playfield wood, maybe even coming out the other side of the playfield. So they had to stop cranking it in. Oh, this makes me think of another thing. This is a perfect example to talk about it. Slotted screws. I despise slotted screws. Whenever I see a slotted screw, it goes in the garbage. Even if it's the proper thread, even if the threads are still good, it goes in the garbage. And the other thing I don't like using on end stops especially is hex head screws. Because if you look at this, Stern in these kind of, on the picture on the right, when they came new, they had 1/4 inch hex head screws. And when you have a hex head screw, you have to use a driver that has to go on the outside of the head. And there was just not enough room to get that driver on to take the end stops off. There was barely enough room. So the types of screws I like to use on flipper end stops are either Phillips, or most of the time there'll be an Allen head screw. And that's the reason those are beneficial. You don't have to put the driver on the outside of the head. So how would you fix something like this when somebody has just completely ruined those threads? Well, you could buy a new base plate. You could continue using a sheet metal screw, an even bigger one the next time you put it together. Or what I always do, and this is quick and easy, there's probably a lot of tips online for how to do this. I won't get into them here, but I'll just braze new nuts on the back of the base plate. And then you're back to like new. Okay, now I want to get into some general tips for rebuilding flipper assemblies. The first one is I like doing them on the bench. I don't want to do a flipper rebuild on a flipper that's in the game. And having them on the bench makes it easy to clean them top and bottom. You can get a good idea. It's easy to check all the screws, all the threaded parts of the base plate. I'm an avid tap and die user. I always think if there's a screw someplace that doesn't go in super freely, I'm getting the tap and die set out. Every screw needs to go in perfectly freely and also be able to hold tightly. And if it doesn't hold tightly, braze a new nut on the bottom. And another thing I like to do right when I clean a base plate is on the bottom of it, I mark which side it is. Because when I overhaul flipper assemblies, often they're not going back in the game. Often they're going in a box, put on the shelf to use as a spare. So if I'm going to that box to replace one in a game someplace, I want to be able to quickly grab the left or grab the right without having to pick it up and figure out, okay, what's the rotation on this shaft. Oh yeah, and the other thing you probably noticed in one of my previous pictures was I like to rewire the whole flipper assembly when I have it on the bench, and I like to put a connector on it. I don't like soldering wires on coils in games, especially a flipper coil, which has a lot of double or triple wires to solder onto a certain lug. I guess as old as I am, I don't like being in that game, being contorted in all kinds of weird positions, trying to solder 3 wires onto a flipper lug. So I always put connectors on them. Makes them modular. It's easy to just swap out the whole assembly. And I'm going to show a picture of what I'm about to say shortly. So I'm going to skip over the second one. But it's important that if you're going to be putting connectors on your flipper assemblies, it's very important that you become adept and good at crimping pins. Because if you're not, you're going to be introducing more intermittent problems into the system. So before you start crimping pins, watch some YouTube videos. Molex had a good crimping guide. It was a set of kind of good and bad crimping techniques. They were just images, but become pretty well versed in how to crimp pins before you start doing this. Otherwise, you'll be causing more problems than you're solving. So here's some of those examples of flipper assemblies that I would keep in stock for various games. They all have a connector on them. They've all been rewired. The wiring is all nice and clean. They have a connector if you need to take them in and out of a game. Easy to do. And the next picture, this is what I was talking about, where I make the 2 wires turn into one. In most classic flipper systems, you're going to have dual power wires because the flipper voltage just loops from flipper coil to flipper coil to flipper coil. So there'll be two power wires on most of them. And two of these 18 gauge wires won't fit in the type of pins I use. So this is the first thing I do when I'm rewiring a flipper in a game. I'll turn those two wires into one. And then that one wire can go right into the connector. So in a typical late 70s, early 80s pinball machine, you'll have a lot of wiring going to the flipper assemblies. In this example, I've removed the flipper assemblies and just left behind the wire. So when you're done shopping out your flipper assembly, this is what you're going to be putting it back into. You're going to be mounting it back in there, plugging a connector in. Easy to take the whole flipper assembly out, easy to put it back in, no more soldering. Ron, how are we doing time-wise? 4 minutes? 3 minutes? I have so many more slides left. Okay, let me go to this really quickly. Required and optional tools for flipper repair. Some of these are pretty basic. Um, there's pretty much just these Allen screws are necessary. I say a slotted screwdriver, even though the slotted screwdriver would only be used to remove screws. I would never use one to put a screw back in. Um, a lot of different files because you'll need to clean up some of those high power switches, the cabinet switches, and the end of stroke switches. And I swear by tap and die sets. I use most of the taps that are listed here regularly. But you're probably looking at that last one, the quarter 28, wondering where would that be used in a flipper system? Well, they're used in a lot of the set screws on the crank arms. I like even making those screws thread in and out freely. 2 minutes. Okay, let's see. I wanted to spend a little bit of time talking about common flipper issues, but maybe I'll just cover one of these since we only have 2 minutes left. And it's one that probably any experienced flipper repair person has encountered. I'm going to talk about the second one, the chattering flipper. You'll hold the flipper button in, and the flipper will just chatter back and forth rapidly like a machine gun. And that is almost always, in fact, I would say that is always a bad coil. The low power coil inside that flipper coil is open. The little wire that attaches onto the lug is broken. In fact, I can't even think of another thing that could cause that chattering flipper. Sometimes you can just solder that wire back on. Sometimes the brake might be further back where the wire goes in the coil. And I think they're coming up with the hook right now. So there's no time for your questions, but if you have any questions or comments, I'll be outside the seminar room. And if you tell them, if I said something here you disagree with, just come on out there and tell me, Mike, this one thing you said is all wrong. This is how you should be doing it. I'm all ears. I always love hearing new things, learning new things.
And we can do a part 2 next year with all your leftover material, right?
That could be, yeah.
So